This is the summary for the bioelectrical signals and systems module, and the goal here is to talk about the key aspects of systems thinking that were involved in this module. Here are 4 of the key aspects of systems thinking, and we'll have 3 more on the following slide. So starting with number 1, having mission, goals, and their relationships to the design objectives. And in our case, you might say that our mission or our goal was to measure a pulse. Now our design objectives for the pulse sensor needed to consider the amount of amplification and filtering that were needed to detect and process a low-level signal that was potentially noisy. So therefore we have the amplification needs and the filtering needs and how they relate to the mission of measuring the pulse. Second, thinking about some of the system-centric constraints, which may be ethical, societal, physiological, psychological, and or environmental, and that can include safety, privacy, and things like cradle-to-grave costs. And in our case, one of the main things, since we're talking about human subjects, could be human testing and how that relates to safety. So human testing, safety. In this case, the sensor is a low power device and it's unlikely to cause harm, but it is still an important consideration to have in general whenever you're doing this kind of work. And we would also want to consider things like reliability and accuracy, since inaccurate data could cause unnecessary concern or miss a health problem, for example. The third one is performance metrics and how they relate to costs and benefits. And an important performance metrics in this case, or metric, is, for example, dynamic range. If we have a greater dynamic range, that's going to increase the circuit complexity and therefore the cost, but it might make for a more useful pulse measurement system. Finally, on this slide, design layers and having appropriate models at each layer. And at the highest level, as we talked about, the pulse measurement system includes the human with the pulse sensor, and the measurement instrument. So our layers might be human plus sensor plus instrument. And the instrument in the lab that you used was the oscilloscope. So we had models, for example, for the sensor that we looked at, and we had models, or we could have models potentially for the instrument. And in order to understand how this pulse measurement system is to operate, we need to understand how these 3 different components interact with one another. Continuing on, we have the subsystems and the components at each layer and their interactions. And we discussed the block diagram for the pulse sensor circuit, which included the photodiode, an LED, a power supply, filtering, and an op amp. And then the op amp was represented as a black box, which of course is going to have many components inside of it. The filtering was shown at the individual resistor and capacitor level. So here I'll just say, as a reminder, the block diagram for the pulse sensor. Number 6 is how information flows between layers, how power, DC power for example, flows between layers, and how the different layers interact with each other. And in this case, we have basically a pulse sensor, and that must detect the pulse. So, seems pretty obvious, but the system doesn't operate if the pulse that's being generated, if that information doesn't flow to the pulse sensor, and eventually that information is flowing to the oscilloscope. Finally, looking at conflicts that result in design trade-offs, and here we could talk about, for example, potentially having more filtering. So more filtering could be done in the pulse sensor if the size and or the cost were not important design drivers, but in order to keep that pulse sensor very small and to keep the cost low, the filtering was pretty simple. So that concludes our discussion of the key aspects of systems thinking for the bioelectrical signals and systems module, and you'll see a similar analysis for the other modules in the ENFUSE collection.